now. Okay, so what this is today is the entire, every calculation that I can think of that you might possibly be expected to know on the IB exam, because there is going to be math on the short answer especially, and even sometimes on the multiple choice. The multiple choice, while you don't have a calculator, you can still do a lot of calculations, and oftentimes you can round to very simple calculations such that you have an easier time calculating. Like 0.09, you can round to 0.1, or 0.9, you can round to 1, and you'll still get the same answer choice for your decisions. But we are going to start kind of in a backwards form. We're at topic 11 and 21 and do the simple calculations there and work all the way back to topic 1. And if we run out of time for stoichiometry, then we can do that either A in class or individually outside of that. And so the first thing, and here is significant figures. Okay, and significant figures math involves two types of math: addition and subtraction, or multiplication and division. And when we add and subtract, we actually don't go by the number of significant figures, we go by place value. Because when you're adding or subtracting, you're usually in the same unit, so the decimal place means the same thing in both of those measurements. The tenths place is the same for both units of centimeters. And so the number of decimal places you have is how precise your values are. So when you have like 4.31 plus 6.8, your answer is restricted by your lesser precise value. So although your calculator will say 11.11, because this number is limited to the tenths, your answer has to be rounded off to the tenths. So you can only record the value as 11.1. With addition and subtraction, I actually like to do it vertically because I think that's the easiest way to see things. I line up all my place values and then I let it decide what it's going to be. So like, for example, if I'm doing 15.4 minus 6.73, when I plug this in my calculator, I will get 7, 6, and then 8. But because the 4 is my least precise, I have to truncate after the 6 and round. So my answer is only 8.7. So with addition and subtraction, I like doing it vertically because it's easy to line up all the place values and then dictate what your answer is going to be. With multiplication and division, it's different though, because in multiplication and division, you are generally going to come up with a unit that wasn't what you started with. Like if you're doing density, you're starting with a mass and a volume, and your new unit is mass per volume. And so those place values don't mean the same thing. A tenths in mass in grams doesn't mean the same thing as a tenths in volume of decimeters cubed. So we can't compare the precision that way. And so when you do this, your answer is limited by the least number of significant figures that you have available in your problem. So if you have something like 4.5 centimeters by 10.2 centimeters, when you type that in your calculator, you get 45.9. But because this number only has 2 and this has 3, your answer can only have 2. So the appropriate value that you would record is 46 in these scenarios. And it would be 46 centimeters squared because your units do change as you multiply the units or divide the units accordingly. Any questions? these calculations I just did and the next ones I'm going to do, these are really kind of popular for maybe the very last multiple choice question and maybe 1 or 2 marks on the paper too, in maybe like a lab question or things like that. But like when I really see this is usually the last question of a multiple choice. If you've done some practice papers, you see that they'll give you values and then you'll have to calculate the correct answer and the correct number of significant figures or place value. And so that's the main thing that you're going to be kind of doing with this. With uncertainty, you also have a separation between addition, subtraction, and multiplication and division. With addition and subtraction, you go by the sum of the absolute uncertainties. So, because again, you're adding 2 units that are the same, and so their uncertainties can also be related to each other. So, if you have a volume of a from a burette of 45.6 plus or minus 0.5 centimeters cubed, and then you subtract 11.2 plus or minus 0.5 centimeters cubed, you'll get 34.4 plus or minus 1.0 centimeter cubed. Now, I know that generally speaking, when you have uncertainty of an original number, when a measured value, you can only have one significant figure. But once you process this data, that uncertainty is magnified because each value has an uncertainty of 0.5. So the maximum uncertainty, even if it's not realistic, is 1.0. Because you always want the uncertainty to be at least like outside of the realm of possibilities so that it includes every single possible value that's realistic. So absolute uncertainty is the exact uncertainty that's associated with that value. Whereas with multiplication and division, you go by the sum of relative uncertainty. Because now you're dealing with different units and you're going to end up with a different unit in your overall answer. And so these uncertainties don't necessarily equate to each other. And so you have to find the relative uncertainty and add them up. So let's say you're trying to find density and you have 4.82 plus or minus 0.01 grams. And you have a density of 1.4 plus or minus 0.5 centimeters cubed. Okay. Well, this is a twofold problem because you have to first calculate this answer, 4.82 divided by 1.4, gets you 3.442857, but because this only has 2 significant figures, your answer can only be measured as 3.4. This part, for relative uncertainty, it's relative to your measured value. So you would do 0.01 over 4.82 plus 0.5 over 1.4 times 100. So it's relative to each value plus 0.5 divided by 1.4 times 100. And you get 35.92%. Generally speaking, you want with larger percentages like that, you can just round to the ones place. Questions about any of this? Okay. The last real calculation on this is IHD, I would say. And I know we talked about it recently in class, but I want to kind of document it here, is index of hydrogen deficiency. And this tells us how many H2 molecules we would need to saturate fully a straight chain carbon. And so this is where you factor in double and triple bonds, and you factor in rings, okay? Each double or triple bond is 1 or 2 respectively, and each ring is 1. So if you're given the structure, you can just count it based on the structure. So for example, benzene, C6H6, has an index of hydrogen deficiency of 4 because you have 3 double bonds and 1 ring. So that is 4 for IHD. But if you're only given the formula, oops, sorry, I need to keep chat open. Apologies. Yes, Alex, sorry, I missed that. You would put the percent in the answer if they were asking that. Some people actually convert it back to absolute uncertainty by multiplying the percentage by the answer and then matching the place values. But yes, a lot of times you'll just keep it in percent. Okay, let me keep chat up. Sorry, for those of you that want to type in chat. So yeah, you can put percent as part of your answer. Now, if you're given formula, then you actually have to go through a process. And that calculation is 2C plus 2 minus H plus N minus X over 2. Okay, because essentially you're trying to think, how many hydrogens would I need to saturate a straight chain version of that carbon? And that's the 2C plus 2. Because for an alkane, the formula is CnH2n plus 2. So 2C plus 2 is the maximum number of hydrogens that I would need if I were just bonding every carbon singly to hydrogens. This is how many I have. This is halogens, which act as the same as hydrogens. And then N are an additional 1 hydrogen, because a carbon in the middle can hold 2 hydrogens, and on the end can hold 3 hydrogens. And N in the middle can hold 1 hydrogen, and on the end, I'm sorry, in the middle can hold 1 hydrogen, and on the end can hold 2. So having just 1 N there allows you to have 1 more hydrogen than you would if you didn't have a carbon there. So that's kind of where the origination of those numbers came from. With oxygen and things like that, oxygen is already factored into the carbon deficiency, because every time you double bond a carbon with oxygen, you lose hydrogen. So therefore, this value decreases, and so it's already factored in. That's why you don't see oxygen in this formula. It's already removed hydrogens from the formula, which makes this minus H smaller, which reflects your index of hydrogen deficiency. Okay. So know that equation, because that is very possibly something that they might ask you about, and you're never given that equation in the data booklet or anything like that. Excuse me. Questions? Okay. Topic 10 and 20 is very kind of light on the math as well. The only main math that I think you'd really have to see, other than like general formulas and stuff like that, is combustion analysis to find empirical formula. So what this is when you're combusting an organic molecule, it breaks up into various oxides, and carbon dioxide and water, namely. If there's nitrogen, you might produce nitrogen as well, but that's pretty straightforward because all the nitrogen has to be in the compound, so you don't really have to do any math with that. So with this combustion analysis, you get complete combustion of this organic compound, normally carbon, hydrogen, oxygen. Okay. If there's nitrogen, usually nitrogen N2 is a product. So whatever mass of N2 you had is how much you started with, because there's no other source for it. But this is the main one. And the idea here is that you have to use the law of conservation of mass. Because the amount of carbon here is the same amount as here. And the amount of hydrogen here, excuse me, is the same amount of hydrogen here, because there's no other source for it in your balanced equation. So what you have to do is calculate how much carbon is in that sample of CO2. And that ratio is always fixed. Every 12.01 grams of carbon are found in 44.01 grams of CO2. That ratio is always true. So if you multiply it by your sample, you'll get the mass of carbon, because that fraction is always true. And same can be said of water, 2.02 grams of H over 18.02 grams of H2O times its sample is grams of hydrogen. And what I mean by sample, just to clarify, is they'll give you the mass of CO2, and they'll give you the mass of H2O, and you'll use that for that. And that allows you to figure out the grams of carbon and the grams of hydrogen. And oxygen, grams of oxygen is the remaining. So whatever they tell you the amount of substance you started with is, you subtract the carbon, you subtract the hydrogen, and then you get oxygen. That's what's left. And once you have all those masses, it's a normal empirical formula problem. You convert everything to moles, and then you convert everything to the lowest ratio, and then that's your empirical formula. We'll probably save that for topic 1 to talk about. And again, I noticed, I think on the topic 10 or 20 test, that in one of the problems I had N, and then I had N2 over here. And for some reason, students didn't want to just assume all that N was over there. They were trying to do something like 14.01 over 28.02 times N2, but it's not 14.01, it's 28.02. 100% of that nitrogen is in your sample. So if I give you a mass of nitrogen, that's your mass. If I give you a mass of N2, that's your mass of nitrogen. So don't overthink that, because even if you do it the way that I've told you, you should get the fact that it's all nitrogen that's in your sample. So don't let that trip you up. Questions? Okay. Topic 9 SL doesn't have very much math either. It's all about balancing reactions, identifying oxidation numbers and stuff like that. And while technically calculate oxidation numbers is math, I don't really see it as something that we need to cover on here right now. That's more of understanding what the oxidation numbers are around there and the new addition and subtraction. The main math is found in topic 19 in HL. And there's 3 major concepts in topic 19 that you need to be aware of. 1, calculating cell potential. Given 2 half reactions, what is the cell potential of those reactions? And the thing you need to remember is the values provided in data booklet are reductions, evidenced by the equation that's written next to those values. So you're always going to have, when you're comparing two half reactions, you're going to be given both reduction values. So therefore, the one that's more positive is the better reducer. And the one that's more negative is the better oxidizer. And if you're trying to figure out a voltaic cell, you want the best reduction potential plus the best oxidation potential. And that way you get your cell potential. And when you're looking at oxidation potential, it's just the opposite sign of your reduction potential. Okay. But so what I like to do is I like to flip the reduction potential for the oxidation and add them together. But sometimes books will say reduction minus oxidation. And like, yes, that is technically true. If you just take the value straight from the booklet, you subtract the value that's going to be your reduction. But I don't think conceptually it's really super easy to remember that. So I just think one of them I'll keep the same, one of them I'll flip, and I just add them together. Because you want a positive cell potential in a voltaic cell, always. If you don't get a positive, then your voltaic cell isn't working the way as planned. And you can see this in this table here. Standard electrode potentials are all standard reduction potentials, because notice here they've written them out in the form of reductions. So Li solid is the best reducer. I'm sorry, best oxidizer, excuse me. Best oxidizer. Li plus is the worst reducer. Fluoride minus is the worst oxidizer, but F2, fluorine, is the best reducer. So you do want to really keep an eye on your species here. And so let's say you're comparing Fe2 plus versus Ni2 plus. Well, Ni is more positive, so Ni is the better reducer. Therefore, Fe is oxidizing. So you'd flip around the 0.45 and add them together, and you get positive 0.19. And that would be your cell potential between these two cells. And you never multiply never manipulate cell potentials by coefficients. Okay. The only thing you can do to a cell potential is reverse it. That's all you can do. A cell potential is an inherent value of that species. It's not based on number of moles. It's not based on number of grams. It's an inherent potential of that species, no matter what amount you have. So the only thing you can do to the reaction is reverse it if you're trying to find the oxidation. Okay, 2. Once you have that cell potential, you can relate it to spontaneity. Okay, and this is where this equation negative NFE comes into play, where it's negative number of electrons transferred, Faraday's constant, 96,500 joules per coulomb, and cell potential in volts. Okay, and the IB does give you this equation, so that's nice. But the IB doesn't tell you how to figure out the electrons transferred here. And so that requires you to be able to look at a balanced redox reaction and look at the number of electrons transferred. And so, for example, let's say you had something like this, and then you had something like this as my two half reactions. Well, to do this, I'd have to multiply this one by 2 and this one by 3 to balance them out. So it ends up being 2Fe3 plus 3Ni yields 2Fe plus 3Ni2 plus. But what you care about is that there were 6 electrons transferred in this process. So therefore, you actually have N equals 6 here, because when you combine the reactions together, you cancel out 6 electrons. That's how you figure out N. That's the key thing that the IB doesn't give you enough information about. They expect you to know it. Again, the IB loves giving equations, but they don't give you enough information that any student could just go up and use that equation and get the answer right. You still have to have knowledge about the equation to be able to get the right answer. And in this equation, the knowledge is how to figure out numbers of electrons transferred. That's the piece of knowledge. Questions? Okay. The last thing is electroplating. And with this, I would encourage you to know a few things. Okay. One, okay, charge is equal to current times time in seconds. Okay. That's one equation you need to have to know. The second equation is kind of a conversion, that 96,500 coulombs is equal to 1 mole of electrons. So if you find out how much charge you put in there, the current times time, if you divide that by 96,500, you'll get the actual moles of electrons you put through the system. And once you have the moles of electrons, you can do the moles of metal because of the mole to mole ratio. For example, let's say it's aluminum. Well, 1 mole of metal is produced when you use 3 moles of electrons. So if I know the moles of electrons, I can figure out the moles of metal because that proportion is always true. And this is reversible as well. If I start with mass of metal, I would convert it to moles of metal, and then convert that to moles of electrons, and convert that to charge, and then use it accordingly in this equation to solve for the amount of current or the amount of time that I would need to run it for. And this also highlights the 3 factors that affect the amount you can electroplate: current, time, and the number of electrons that metal needs. If that metal needs 3 moles of electrons or 2 moles of electrons, you'll be able to make more metal with the 2 moles of electrons metal. So those are your 3 major factors here: the charge of the metal, which implies the number of electrons, and then the current and the time are the main factors that affect the amount you can electroplate. Questions about this? You can put a question in chat, or you can turn on your microphone. Okay. Okay. Topic 8 and 18. Okay. This is acids and bases. And I'll be honest with you, while this is a really complicated topic, a lot of that is mostly conceptual. The math is kind of fairly straightforward here. You have 3 major things you have to be able to calculate. Okay. Well, actually, I guess you'd group kind of 2 of them into one, like as in 1A and 1B. Okay. Like 1A is calculate pH of strong acids or bases. Because strong acids or bases, they dissociate 100%. So if you want the pH as the negative log of H plus, or the POH as negative log of OH minus, then it's pretty straightforward. It's proportional to the molarity of the acid or base that you have. And so like if you have 0.01 molar HCl, that means you have 0.01 molar of H plus. So therefore the pH is equal to negative log of 0.01, which is 2. But conversely, if you have 0.05 molar of calcium hydroxide, because there's 2 hydroxides in there, you have to multiply the molarity by 2 because you actually make twice as much OH than you started with. So that's 0.1 molar of hydroxide, which then makes your POH negative log of 0.1, which makes your POH 1, which then makes your pH 13 at 25 degrees Celsius. Assuming you're at 25 degrees Celsius, it adds up to 14 overall. And that would be SL or HL, I should clarify. That's SL and HL comprehension. And a side note here, each pH unit is a factor of 10 in concentration. Okay. So every time you change the pH unit by 1 unit, you're changing the concentration of the solution by a factor of 10. If you're going from pH of 5 to 4, whatever molarity of acid produces a pH of 5, the molarity to produce a pH of 4 will be 10 times that. Or if you're going from 5 to 3, that would be 100 times as concentrated to get that same pH. And so do keep that in mind as another kind of simple concept as well for SL and HL in these calculations. One B is the HL aspect, and that is calculation of weak acids and bases. Okay. And this is where you introduce the concept of Ka and Kb, because weak acids and weak bases dissociate partially. So now you have an equilibrium that you are dealing with. And so, for example, a Ka of, I don't know, CH3COOH. When I say Ka, I mean acting as an acid with water. So the reaction of it with water would be this. Notice 1, the double arrow, 2, the donation of the proton in here, which makes Ka CH3COO minus times H3O plus over CH3COOH. Oops, it's too many O's here. So that's your equilibrium constant expression, and that's the concept that you're going to use to be able to solve for Ka or solve for the pH or POH, depending on your solution. Right? Because you'll have to do a Rice chart. You'll be given the molarity of ethanoic acid, and you'll have to solve for the pH by figuring how much it dissociates by using Ka. And again, pay real close attention, because if you're dealing with a Kb, like for NH3, it's the same idea. It reacts with water to form a conjugate acid and OH minus. But if you're dealing with this, you're dealing with OH minus, which can only let you solve for POH, which then can solve for pH. That's where a lot of students get things wrong, because they just assume that whatever X is when they're done with the rice chart, that's H plus. So then therefore negative log of X is pH. It's all about the context of what your problem states. And again, you can also kind of mentally check it as well, right? If you get a base and your pH is 4, you did something wrong, because there's no way a base will ever have a pH of 4. The worst it could have is 7 if it was completely diluted and there was like an infinite amount of water. So there's no way a base can have a pH of less than 7, which is neutral, and no way an acid has a greater pH than 7, which is neutral. The second thing is neutralization. And to be honest with you, now that I think about it, this would also be in topic 9 for SL with redox titration. But we'll put it here anyway, because a redox titration and a acid-base titration are pretty much the same thing. You have molarities and volumes of both species, and you're trying to find out the unknown molarity of one of them. So you have volumes of both species, molarity of one, and then you have to find the unknown molarity of the other. So whether it's redox or acid-base, it's the same concept. You need a balanced equation, and you need to use that to convert from one substance to another. So you might have something like this. And you might be given the volume of H2SO4 and then the volume of NaOH needed. And the molarity of the titrant as well. And you'd have to solve for the molarity of your acid. Now you could do it normal stoichiometry, solve for the moles of NaOH, solve for the moles of H2SO4, and then divide it by the volume, and that works fine as well. If you're a person that likes proportions, I find that the easiest way to do it is this proportion here, where this is the mole to mole ratio. And then on the left is the molarity times volume over molarity times volume. A couple of things about this. One, you don't have to change the unit of volume because they're both centimeters cubed, so the proportion works out fine. Two, it reminds you that you need a mole to mole ratio in here. And then three, essentially it's just cross multiplication with a lot less work. You could also do this with redox. It doesn't have to be acid and base. It can be the oxidizer and the reducer. Still works the same way. But if you like to do fact label, then you would do that. You could do very well do 0.030 decimeters cubed times 1 decimeter cubed is 2.0 moles of NaOH. And then 2 moles of NaOH is 1 mole of H2SO4. And then the volume of this you divide by. So once you get the moles of H2SO4, you can divide, because that way your units are correct. You want moles over decimeters cubed. Everything else cancels out. And so you could do it either way. You could do a proportion method as well. But if you're looking for a kind of a direct way to do it, I like that kind of super portion here to be able to figure it out. But if you don't feel comfortable and you've already been doing it the other way, then go ahead and do it the other way. Questions about any of that? Topic 7 and 17, equilibrium. Okay. There is the same kind of Rice charts as there is in topic 8 and 18. But depending on the level, will tell you SL or HL will tell you what extent you have to be able to do them. And so let's say you have something like this. Okay. Notice A, the double arrow, and the reactants and products here. I find when you're doing an equilibrium problem, it's always best to kind of write out all your values in the table, because you can kind of tell what you have to do based on that type of table. For example, if you have values here, here, and here, then you're already done, because K is equal to C over A times B squared. So if I have n values for everything, then I'm done, because I just need to plug those values into K. Now, if I have initial value, and 0 here, and then I have one of the final values, like let's say this value, I can solve for these values because I know what this X is going to be. Because I can fill in the rest of the chart. If I have one final value and one initial value that I can solve for the change, I can fill in the rest of the chart, and then I can solve for K. Okay. The challenge with HL is that I may only give you the initial values. And if I give you the initial values, then you're going to have to substitute X's in there, and you might have a perfect square or a 5% rule, okay, where you'd ignore the minus X or plus X and solve for it without there because K is so small. Remember, 5% rule is when K is small. Because if it doesn't dissociate, if it doesn't react that much, then most of it stays on that side. So the change in X is insignificant on the side that you already have quantities of. Questions about that? So yeah, really, I find if you're doing an equilibrium problem and you're given an equilibrium reaction and you want to find K or find the N equilibrium values, write the Rice chart out and fill in what you know. And if they don't give you an amount for for the initial, you assume it's 0. And when you do all of that, you'll see what you're able to solve for in the problem. Can you solve for the N values? Are they already given the N values? Read the question very carefully and see where the values they give you belong in this Rice chart. And that will really help you see what you need to be able to do. Questions about that? Okay. Okay. Topic 6 and 16 is rate law, a rate of reaction and kinetics, and for higher level, rate law. Now, for SL, I think the major things that you'll be kind of dealing with is calculating rate, which is the change in concentration over the change in time. And so you may be given values for this, but you may also be given a graph and you may be expected to find a point and find the tangent to that point here. And that would be, the slope of that would be your rate as well. So for SL, most of it is just calculating rate based on a given experiment or things like that. With higher level, there is a lot more calculations in this, and you're starting to see a trend, I would say, in the SL versus HL material. Like I've said before, a lot of the math is reserved for HL because the IB has decided that math is what separates kind of the challenge in chemistry in this. And so in 16, you have to do rate law and calculating order of each reactant. Okay. And this is where you're given concentrations and given rates or even times to do this. And you're looking at how does a change in concentration affect rate. So you're looking at what exponent for which the change in concentration happens, does that affect the rate in the correct way? And so, actually, let me pull this up because there was one I wanted to. Oh, I hope I didn't delete these. Hold on a second. Was it this one? Oh, let me pull this up. I thought it. Ah, here it is. Yeah. Okay. Actually, this isn't exactly the one I want, but I'll use this one for now. Wait, where'd it go? Okay, that'll be fine. So this is an example of what they might do. Okay, they'll give you concentrations and give you rates, and you'll need to see how does the concentration relate to their rates. And so whenever you do this, you have to make it such that one of them stays constant and the other one doesn't change, if possible. So in this example, if you're trying to figure out the C3H7Cl, excuse me, order, you would choose reaction 1 and 3 because there your rate of OH minus is constant. So that means that whatever you did to C3H7Cl is what you did to the rate. So if you look here, oh, let me stick with this color. This increased by a factor of 3. And this increased by a factor of 3. So therefore, when C3H7Cl increased by a factor of 3, the rate increased by a factor of 3. Therefore, the exponent for C3H7Cl has to be 1. So it has to be first order here. So we know the exponent for this is 1. Now, the tricky part of this specific question is that notice that there's no way that there's no experiment where C3H7Cl is constant. So which is why we needed to figure out the exponent of C3H7Cl first, because we have to remove that effect on the rate before we can talk about the OH. And this is where we talked about how setting up the proportion is a good way to go, because it doesn't matter which one. We'll choose experiment 1 and 2 for this. Okay. So experiment 2 is 1.3 times 10 to the negative 3 over the rate of number 1, which is 3.1 times 10 to the negative 4. So that's rate 2 over rate 1. Now, the concentration of C3H7Cl is 0.10 over 0.05 raised to the first power, because we know the exponent now. With OH, it's 0.2 over 0.1 to the y. We don't know what that exponent is. So essentially what we're doing is we're removing the impact of C3H7Cl before we can solve for the impact of OH minus. And so this ends up being 4. And this is 2 to the first times 2 to the y. So then 2 to the y is equal to 2. So y is also equal to 1. So it's first order in both of these experiments. So the rate is equal to K times C3H7Cl raised to the first power times OH minus raised to the first power. And that's my rate law expression. So you do have to be careful. If you don't like kind of just like messing with stuff and like just kind of remembering a lot of stuff, if you do it this way, it's always foolproof. Like if you have one that's the same, then it'll cancel out and it won't matter. If you want to do it this way every single time, that's okay. Even for C3H7Cl, you could do that. You know, you could do experiment 1 and 3 and be 9.2 times 10 to the negative 4 over 3.1 times 10 to the negative 4 is equal to 0.15 over 0.05 to the x, 0.10 over 0.10 to the y. That cancels out, and that becomes 3 is equal to 3 to the x. So x equals 1. So you can do it that way for everything. Now, I saw on another paper, they're very tricky about this. And I don't know if it's tricky, but it's kind of detail oriented. Sometimes they won't give you rate and they'll give you time. And that is a little bit more confusing because you're used to a rate and that's per unit time. But if they give you time, then rate is equal to 1 over time. Because if the time is going smaller, then the rate is happening faster. So it's very deceptive if you see a time of 40 seconds and then 20 seconds. Well, you can't do the multiplying factor unless you inverse those values, because it's really 1 over 20 and 1 over 40 is the rate, where 1 represents the complete reaction. So careful with time on here. I don't know if I have that question on here because I know someone asked about it. I saw this in a different paper too. No, it's not that one. I can't find it. I don't remember which paper 2 it was, but there was a paper 2 where they give you time instead of rate. And you have to remember that, again, rate is equal to 1 over time. So you'll need to convert those times to fractions, or you can just say, well, if it's half the time, it's double the rate. You can think of it that way as well. But either way, that is the way you want to tackle this. Questions about that? That was a lot of stuff to just kind of look at here. Any questions about that?
Yeah.
Yeah.
Why did you put raise the 0.10 over 0.05 to the first power in the
And the blue on the right, right, Erica? Yeah. So we raised it to the first power because we'd already solved for the exponent of C3H7Cl. And we knew it was the first power. So we knew that if this changed, that the change impact would be to the first power because we solved for that in the previous sample. Because we could find two experiments where OH stays the same, we could solve for the exponent of C3H7Cl, which then allows us to solve for OH because we can remove this factor from it. And so that exponent came from us solving for that earlier in this scenario here.
Okay, thank you.
You're welcome. Good question. So yeah, they will never give you a scenario where you can't find there are no constants, because that's impossible, because then there's way too much stuff going on. But you should at least be able to find the exponents for everything except one of the species. And if you can't find it for that one species, then you can use all the other exponents to solve for that species by doing something like we demonstrated here. Okay. So yeah, this exponent 1 comes from the fact that we were able to solve for the exponent of C3H7Cl first, because OH stayed constant in trials 1 and 3, so we could figure that out. Last thing in topic 6 and 16, the Arrhenius equation. Okay, natural log of K is equal to negative EA over R times 1 over T plus natural log of A. Again, the IB gives into a lot of different scenarios. It just depends on what information they're giving you for you to be able to do it. But I like it in this way because this is the slope equation. So if you graph natural log of K versus 1 over temperature, you'll get a line, and that line is equal to negative EA over R, and EA being your activation energy. Okay. So, and then the intercept here being natural log of A, which is your frequency factor, which takes into account orientation of the particles. Because at that point, 1 over T is essentially temperature's infinity, so every particle has enough energy to react. So it's no longer about the energy, it's about the orientation and collisions. But so this concept is based because temperature increases the rate of reaction, which is reflected by K, because if you're only increasing temperature and your rate law expression is K times the concentrations, well, temperature doesn't affect the concentrations, so it must affect your K, your rate law constant. And so it doesn't happen linearly, it happens kind of exponentially. So if you had your K versus temperature here, it looked like kind of like this. And so scientists ended up linearizing that with natural log of K versus 1 over T to be able to figure out what the activation energy of a given reaction was. And if you're reading this, I would just say, keep an eye on the units of the x-axis. Again, I say it specifically for this graph, but you should always pay attention. But this graph specifically, I find, is the one where students get the value of the x points incorrect, because sometimes it says 1 over T times 10 to the third, or 1 over T times 10 to the negative 3. So please be really careful about those units, because you don't want to miss your answer by a factor of 1,000 because you read your axes wrong. That's a skill that the IB expects you to have, is reading graphs, but they're never going to actually have you read a graph just straight up. They're going to apply that into other concepts like this type of graph or other rate of reaction graphs as well. So keep that in mind. Questions? Okay. We're going to take maybe about a 10-minute break here. We're about halfway through. Topic 5 is kind of huge, but topic 4, there's only really one thing I want to talk about, and that's Lewis structure calculations. And then topic 3 doesn't have much math. There's a little bit of energy in topic 2, and then there's gas laws and limiting reactant, empirical formula, and stoichiometry in topic 1. And we'll kind of see how far we get on that today. And so, because hopefully a lot of that is review from previous years, but we will go over that as best as we can. So I'm going to pause the recording right now for about 10 minutes. And so it is now 10:09. And so then we'll resume at about 10:19. Okay, back from break. Topic 5 and 15. Okay. Energetics. I would say this is one of the biggest topics, especially for SL students, because there's so much math in there that they're bound to have a question from this topic because there's so many calculations that are present in here. And so, especially, I would say in HL2, if they're going to test SL students on it, they'll incorporate those types of questions in the HL test too, because like I said before, a lot of the SL and HL tests overlap. What they do with the HL test is they remove a couple of the SL questions and then add HL content in there. So maybe SL calculates the enthalpy of reaction with bond enthalpy, and they do enthalpy of reaction with enthalpy of formation, whereas HL does enthalpy of using bond enthalpy, but then they calculate Gibbs free energy and entropy as well. And so a lot of the stuff does overlap between the two. But the main focus in topic 5 is enthalpy and understanding the multitude of ways to calculate enthalpy. And the first one we'll talk about kind of briefly, even though it's probably the most important one, is Hess's law. Okay, Hess's law essentially states that the sum of the enthalpies of reaction equal the sum of the reactions. Essentially, if I add reactions together, I can add their delta H's together, and therefore the delta H sum will equal the sum of those reactions. Okay, and that's concept, and that's where you are having to reverse reactions or double reactions or halve reactions. So the main concept of Hess's law is really that understanding that this is some value of A, and this is negative A, and this is 1/2 A. So whatever you're doing to the coefficients, you do to the delta H values as well. Okay, and then you still add them all up such that you get the overall reaction. So manipulating reactions is the kind of core dynamic of Hess's law. And the IB will only give you reactions that you need for Hess's law. And so what I always try to do with Hess's law is try to find the unique species in each one of the mini reactions that helps me reach the overall reaction. And so, like, for example, I think I have a practice problem here. Because you'll find that every smaller reaction has a species that's unique to it. Is that the one I want to use? No, I don't think I want to use that one. Actually, you know what? No, I will use that one because that brings up an interesting question here. Okay. This is an example of a Hess's law problem. Let me crop this a little bit. Okay. Now, again, if you look at this reaction, each reaction has something that's unique to it that matches the overall reaction. For example, here, this H2SO4 liquid is only found in this reaction, which means that if it's in the overall reaction, you have to make this reaction match that. And you look at it and it's on the wrong side. So therefore, this has to become positive 235.5 so that it matches the overall reaction, because there's nothing to cancel it out. There's no other reaction that includes that. So you have to use that equation that way. So that's what I mean by finding unique things. Find something that's only in that reaction, match it to the overall, and then everything else will take care of itself. For example, here, SO3 is on the correct side with the correct coefficient. So negative 207 stays the same. The gas is on the correct side, so this will stay the same. Okay, and so you add all these values together, 235.5 minus 207 plus 44, and you get check here, so what is it, like 28 or 27.5 plus 44, it's like 71.5, so 72 kilojoules here. Okay. Now, one conceptual thing that I'll add here is that notice phase changes do affect your enthalpy of reaction. And this value would be very different if you didn't have the phase change between liquid and gas, if you had just liquid water here versus gaseous water, because you have to absorb more energy to turn something to a liquid to a gas. So the energy of this reaction is 72, but the energy of the reaction without turning it to gas is only 27.5. So it becomes less energy you have to absorb into that. And conversely, for combustion reactions, if you're producing gaseous water instead of liquid water, that negative value is going to become less than it normally is, because you have to add that extra energy. You have to add those 44 kilojoules back in there from your negative value. So keep in mind the phases do matter, and that will affect your value overall, conceptually speaking. Questions on that? Okay. The second manner is using enthalpy of formation. And we'll write the whole thing out. Standard molar enthalpy of formation. Understanding what that means will actually help you remember how to actually solve these problems. And I find that that's a really kind of good tip for that. Knowing what an enthalpy of formation reaction is like. And so let's say, even like something like this, let's do H2SO4 yields SO3 plus H2O. Let's say that's my overall reaction. Well, for this reaction to happen, I have to create H2SO4. Well, I mean, I have to know the formation of H2SO4. I have to know the formation of SO3, and I have to know the formation of H2O. So this is A, B, and C. Now, because it's formation, notice that the species that are formed in the overall reaction are also the species that are formed in the enthalpy of formation reactions. So those two ones will stay the same. The ones that aren't being formed, the ones that are being broken up, become the opposite. So this is B plus C minus A, or otherwise known as products minus reactants. Now you have to do the coefficients as well. Don't forget to multiply by the coefficients, but that's the main idea. And so instead of memorizing products minus reactants, I just go pick any substance in the reaction and write an enthalpy of formation for it and go, okay, where is that substance in my enthalpy of formation reaction? okay? If it's on the product side and in the overall reactions product side, that will stay the same. If it's on the reactant side, then it'll become negative of what I have. So therefore, it's products minus reactants. The products are on the correct side. The reactants are on the wrong side, which is why this is products minus reactants. So I find that having a justification for the way you do it instead of blindly memorizing P minus R and R minus P will ensure or minimize the chance of you getting it wrong. Way too many kids, like I've said in class, gamble on a coin flip because half of these are products minus reactants and half of these are reactants minus products. And so it's all coin flips to see whether they have it right or not. So understanding this will minimize your chance of getting it wrong and improve the probability odds in your favor. Okay. So enthalpy of formation, everything's formed. So if it's formed in the overall reaction, then that stays the same sign. If it's not formed in the overall reaction, then that turns the opposite sign. I think that's another way to say it, that you can think about it as well. Questions about that? Okay. Standard molar enthalpy of combustion. Okay. Now, unlike, oh, my standard symbol kind of got away from me there. Okay. Unlike formation, what we're talking about is combusting something here. And so let's say we have a reaction like this. And we're trying to solve for this delta H using enthalpies of combustion. Well, for this, you have to combust each species. So you combust C2H2 plus O2 yields CO2 plus H2O. So that's 2, and then that's 5 halves. H2 plus 1/2 O2 yields H2O. And then C2H4 plus O2 yields CO2 plus H2O, 2, 2, 3. If you notice now, though, in combustion, everything you want in your overall reaction is on the reactant side. So therefore, the reactants will stay the same, but the products will have to flip. So the C2H4 has to flip, so it's A, B, and C. So this becomes negative C, which means A plus B minus C, which is reactants minus products. Okay. So kind of a straightforward way of memorizing or remembering which one's which here. Think about what that reaction stands for and write one out and go, okay, this is reactants minus products because all my reactants are on the right side. The one before is all my products are on the right side, so it's products minus reactants. Questions? Okay. Bond enthalpy. Okay. This one, I think the IB likes the most because it takes into account various pieces of knowledge that you have to know to be able to do this. And what I mean by that is, one, you have to draw Lewis structures. Two, you have to understand what bond enthalpy is. And then three, you have to understand which side is endothermic versus exothermic. So I think a lot of times if the IB is going to ask you about enthalpy, they're going to use this because you can do kind of two birds with one stone. They can test you on Lewis structures within this bond enthalpy, and then they'll know whether you can do it or not. Okay. And so this is like a 3 or 4 mark question, but 2 of the 4 marks are really Lewis structures, and the other 2 marks are calculating bond enthalpy when it comes down to it. I know that's not the way the mark scheme works, but that's really what they're testing you here. Okay. So with bond enthalpy, I strongly suggest that you draw at least one of each structure out in your problem, because it'll minimize a lot of issues that students have. Okay. And so the biggest issue I see students have, let's see. Is counting bonds. And if you don't count bonds right, then you won't get the question right and you'll lose all 3 points. And that's a significant chunk of marks on your test that you shouldn't be missing. And so what I do is this: I draw one of each of these molecules. Okay. And then I establish how many bonds are in each one of those molecules. I won't worry about coefficients yet. I'll use that later. So in one of these molecules, I have 1 C to C double bond and 4 C to H bonds. Here, I have 1 O to O double bond. Here, I have 2 C to O, double bonds. And then here, I have 2 OH bonds. Okay. Once I have that established, then I put my coefficients in front: 1, 3, 2, and 2. Because the biggest mistake students make is they use coefficients right away without considering the formulas, the Lewis structures. For example, they'll see 2 CO2 and they're like, oh, I have 2 C double bond O's. No, you have 4 C double bond O's, because each carbon dioxide has 4, and each water, oops, sorry, I almost wrote it there. Each water has 2, so 2 H2Os is actually 4 OHs. Oops. So that's the first mistake students make. The second biggest mistake is they draw the Lewis structures wrong. Because when they draw Lewis structures wrong, then you can't get the value overall right. Because if you do a single bond O for O2 versus double bond, your numbers will never be right. Now, you might get the product side right, but you won't get the reactant side right, and you won't get the overall number right. So you've lost 2 out of 3 marks already. A couple of these molecules you want to keep in mind, right? Oxygen, O2 is double bonded. N2, that's a big one that a lot of students forget, is a triple bond. And that triple bond has a significantly larger value than any other end-to-end double bond. And so, or end-to-end single bond. And so that's the second mistake students make. They don't draw the Lewis structures correctly. So 1, they don't count the bonds correctly because they don't draw Lewis structures out. 2, they draw Lewis structures out, but they draw them incorrectly, which means they get the wrong bond enthalpies, and then they get the wrong value overall. And if you look at the data booklet here, there is kind of a cross table for this. Okay. And all the single bonds are the top in this cross table. So C to H is 414. O to H is 463. So I'm going to put some of those in here. So C to H is 414. O to H is 436. Oh, 463, sorry. Little backwards moment right there. Okay. Double bonds and triple bonds are down at the bottom. So there's a 614 for a C to C double bond, 498 for an O to O double bond, and then 804 for C double bond O. Okay, so 614, 804, 498. Which one did I get it wrong? 804, oh, I did get it right. Okay. I don't know why I have this plus sign here anymore. Okay, so 1 mark for summing up the left side correctly. One mark for summing up the right side correctly. And then here's the idea. A bond enthalpy is positive because it's endothermic, because you're breaking the bonds. When you're forming the bonds, the reverse reaction is occurring, so you're actually releasing heat. So when you make a bond, you release heat. When you form a bond, you break, when you break a bond, you absorb heat. So therefore, on the left side, the reactants, you're absorbing all the energy to break all those bonds. But on the reactant side, you're making new bonds, so you're releasing energy. So the right side is negative, and then you add them together. So 3764 minus 5068. And it is negative 1304 kilojoules. Some people will say reactants minus products. That's fine. If you don't want to change the sign of the value and just do reactants minus products, that's fine. But if you want to think about it in actual endothermic and exothermic terms, the right side is negative, the left side is positive, and you add them together. And this, I should say, let me correct this. This should be kilojoules per mole of C2H4 because there is only 1 mole here. You have to be careful. Sometimes the IB will give you a reaction where you have 2 moles of C2H4 and you calculate the enthalpy of reaction, but then they ask you to calculate the molar enthalpy of reaction. So you'd have to divide that value by 2 to get the molar enthalpy of reaction here. Okay. Another surefire way to kind of quickly check if you're right or wrong is that this is a combustion reaction. And so if you get a positive value for a combustion reaction, you definitely did something wrong, because all combustion reactions are exothermic. So if you got a positive value, then you did something wrong. You need to reevaluate your calculations or your bonds or whatnot, because you should never get a positive number for a combustion reaction specifically. Other bond enthalpy reactions, yes, maybe you get a positive number, but for combustion, for sure, that should be a red flag for your answer if you get a positive number for your enthalpy of reaction. Questions on that? Okay. The last delta H is calorimetry. And I saved calorimetry for last because it's kind of the different one compared to Hess's law and enthalpy of combustion, enthalpy of formation, and bond enthalpy, because really all those are all just Hess's law in different states and different types of reactions you're using for Hess's law. Calorimetry is a very unique kind of experimental measurement. And when I say experimental, I don't mean like it's a test, like it's a lab experiment. I mean, like you actually can perform this in a lab and measure the values for this. And so the focus here is generally we're dealing with solutions, namely aqueous solutions. So we're dealing with water. So in these scenarios, you are going to use Q is equal to MC delta T for calorimetry, but you have to remember that Q is of the water, masses of the water, specific heat of the water, and change in temperature of the water. Because this is one of those scenarios where the IB gives you an equation, but doesn't give you enough information to be able to use that equation without your own prior knowledge. Because a lot of students will see mass and they'll just scour the question for a mass and use it. Whereas we know that this is usually given to you in terms of volume, because we don't measure water in mass, we measure water in volume. And so it's usually given centimeters cubed, and we have to know that 1 gram of water is equal to 1 centimeter cubed. So the ones in the know, the students in the know, will look for the volume of water in their problem and then just assume that's the same mass in grams. That's where a lot of students make mistakes. That's the number one mistake that students make, is they use the wrong mass for it, which throws off all the values and all the calculations for this. Okay. So namely, it's the mass of water is not directly given to you. They give you the volume, and then they will say, assume the density of the solution is the same as water, which is this. That's the density of water. And so you'll need to use that factor into calculating these problems. Okay. Now, once you figure out Q of the water, that's the opposite of the Q of the reaction. So whatever's happening to the water, temperature going up, the water getting hotter, that means the reaction is releasing heat to the water, and that's why that occurs. And so you have to remember that the sign is opposite for the Q of the reaction. And when you divide that Q of the reaction by moles of reactant, that gets you enthalpy. Okay. And so that's how you solve for enthalpy here, because your enthalpy for any reaction should be the same no matter what. Your Q varies because you're adding different amount of reactants you're using in the problem. So it might be releasing more or less heat, but the ratio of the heat to the amount of reactants you use should always be the same. Questions about that? So this is moles of reactant, because often they'll give you the mass of the reactant in the problem, and then it's your responsibility to convert it to grams. Okay, give me 1 minute, I'll be right back. So with calorimetry, that's kind of the main idea, the moles of reactant producing an X amount of energy, which then that ratio always ends up being delta H. So conceptually, we can talk about that a little bit later, but calculation-wise, it's fairly straightforward with that type of question. Now, HL, you get into entropy and Gibbs free energy. And I just remembered that we didn't do delta G for K, and I'll keep that in here as well. That's supposed to be in topic 7. But so here we have entropy. And with entropy, you can talk about it qualitatively, like where it changes from one state to another and things like that. But you may have to actually solve for entropy, and you treat it like enthalpy of formation, because the entropy is essentially the disorder or the energy it would take to organize that one species in that state. And so what you do is you do products minus reactants here for entropy. So that's how you would calculate the entropy. You do the products minus reactants, just like enthalpy of formation. The only difference is for enthalpy of formation, elements is equal to 0, and S, not delta S, I should say. S of elements is greater than 0. There is no such thing as S being less than 0. Delta S can be less than 0, but there's never a time where S is less than 0, because when S is 0, that's absolute 0. So any substance that's above absolute 0 has some disorder to it, some measure of entropy. So S itself won't change, but delta S could be negative based on the products minus reactants scenario here. The main idea and the use of entropy is to apply it to this equation here. This is your Gibbs free energy equation. And the main idea here for calculation wise is units. And I can't stress enough that units are one of those common mistakes, those quote unquote silly mistakes that students make oftentimes, where delta H is in kilojoules, temperature is in Kelvin, and students forget that this is in joules. So we need to divide this term by 1,000 to get it in kilojoules so that your delta G will also be in kilojoules. And so that's really, really important to this concept here. And that's where a lot of students make their mistakes on the calculation. They'll get S and they'll get delta H, and then they'll forget to convert because they didn't write the units out and they just blindly, again, this is another scenario of the IB giving you an equation, but not tell you every single detail about the equation so that any student can get the correct answer. You still have to know the knowledge and you still have to be cognizant of the units of delta S so that you don't make a mistake and get the wrong answer. So really key idea here with delta G. Now, the one I forgot for topic 7 was delta G is equal to negative RT ln K, where again, it's more of a kind of a plug and chug equation where R is the gas law constant, T is the temperature in Kelvin, and natural log of K is natural log of the equilibrium constant. And you have to pay attention because again, R is in joules. So if you use this equation, delta G will be in joules instead of kilojoules. And the IB might ask you to solve for it in kilojoules. So you would get it partially wrong if you wrote it in joules versus kilojoules, because if they explicitly ask for a unit, you have the number that you write down, they assume is in the correct unit. Even if you write the right unit next to it, that's not what the question is asking. So you will get deduction points for that. So if you write 1,000 joules when they want it in kilojoules, they're treating it like you wrote 1,000 kilojoules, and that's incorrect. Questions about this? Okay. Topic 4 and 14, bonding. Okay. Now, for Lewis structures, this isn't directly a math calculation that you'll have to do, but it is something that I find is really helpful because I think a lot of students struggle with writing some of these structures out. And so I want to bring this kind of to y'all's attention again about solving for Lewis structures. And so you have I call it like the calculated or math number of pairs. So you will have to calculate how many pairs of electrons you have to work with in this problem here. And that's all you can use for your shape. And so what that means that if you draw a test structure out, you have to make your test structure match your actual your budget of electrons that you actually have. And so here, for example, and then you have, so for example, let's say you had NO3 minus. That's a kind of a strange molecule that isn't necessarily obvious here. NO3 minus. Well, N has 5, oxygen has 6, and there's 3 of them, and -1 is +1 electron. So that's 24. So that's 12 pairs. Okay. I draw a test structure where everything has a single bond, and if you have more than 4 valence electrons, you get an octet. So if you have more than 4 valence electrons, you're given an octet. If you have less than 4, you just only put the bonds, no lone pairs. So we draw a test structure out here. Everything has a single bond. Everything has an octet because nitrogen has 5 valence electrons, oxygen has 6. This structure has 13 pairs of electrons, and that doesn't equate to what we actually can afford. So what that means is some of these lone pairs aren't actually lone pairs. They exist as a bond in the real structure. And when you have one more pair than you're supposed to have, then that means one more bond. And so here's the issue with this. You need to get rid of this and get rid of another lone pair and make a double bond somewhere. But the problem is, which oxygen do you do? Well, they're all the same. So what that tells you is you have resonance, because the double bond could go here, or it could go here, and it would still all be equivalent. So what happens is it interchanges between these 3 states. Oh, sorry, -1. That's resonance. And so with that, you're able to kind of understand why this structure can't be represented by one Lewis structure. That was a multiple choice question that showed up on a couple of exams, is which of these structures can only be represented by one Lewis structure? Well, what they mean by is which of them do not have resonance. And NO3- is kind of one of those resonance structures that isn't common, like benzene or ethanoate or ozone, but it's still in that grouping. When you actually draw it out, you'll realize that. So really important to kind of use math there to solve it. Questions on that? Now, one more thing. Actually, I'll do 2 more things. This one is not explicit, but I think it helps you explain a lot of things SL or HL like, and that's bond order. Okay. Bond order is essentially kind of showing the relative strength of a bond. A single bond has a bond order of 1. A double bond has a bond order of 2. A triple bond has a bond order of 3. That's pretty straightforward. It's when you have something like NO3 1- where you may not be able to see what the actual bond order is because there's resonance. And so the way you calculate it is you do the total number of bonds divided by the bonding regions. And that means that essentially this NO bond is equivalent of 1.33 bonds. So it is stronger than a single bond, but weaker than a double bond. And so its bond length should fall in the middle of that. And you can use bond order as an argument for explaining bond length and bond strength as well. So it's definitely a nice kind of thing to have in your arsenal when you're trying to explain concepts in here. So you take the number of total bonds between the 2 atoms in question and divide it by the total number of atoms bonded to that atom in question. So like here, there's 4 NO bonds, but there's only 3 NO linkages. So it's 4 divided by 3. Ozone, there's 3 total bonds between O and O, but there are only 2 O linkages. So the bond order of ozone is 1.5. Okay. Questions about that? like I said, that's not something that's directly in the IB curriculum, but I think it does help you explain, and they do sometimes talk about it in your mark schemes as well. And so wanted to make sure we talk about that. Okay. The last thing that we talk about in topic 14 is HL. And that's formal charge. Okay. Formal charge helps identify the, well, preferred Lewis structure from multiple options. Sorry, my handwriting is getting really bad right now. Okay, there are some Lewis structures that can be written more than one way. And if that's true, not like in terms of resonance where the bond is delocalized, I mean, you can put a double bond somewhere or a triple bond somewhere and it still be a legitimate shape. When that's the case, this comes down to formal charge, and this formal charge helps you figure out which one's the best, more stable structure. Formal charge is the number of valence electrons minus the bonds minus the electrons remaining. So that's like a lone pair is 2 electrons. Okay, so whatever electrons are also around the atom that aren't in bonds, you subtract that. And each electron is 1 electron, not each lone pair, each electron. Okay, so for example, one of the most common ones they use is SCN minus as an example for this, because technically, if you draw SCN, it is technically appropriate. It meets all their criteria if you draw it all these 3 ways, where you have a triple bond on N, a double bond on both, a triple bond on S. They're technically all right, technically. But one of these is better or more preferred than the others based on the formal charges. Okay, and so you want you can write this on the side. I just don't have space here. You want formal charge to be as close to 0 as possible. Now, the sum of it equals the overall charge, but you want them to be as close as possible. So for example, here, S has 6 valence electrons normally. It has 1 bond. It has 6 electrons remaining around it. So it has a -1 charge here, or 1 negative charge. C has 4 valence electrons. It has 4 bonds and 0 extra electrons. So that's 0. N has 5 minus 3 minus 2. That's 0. Here, 6 minus 4 minus 2 is 0. 4 minus 4 minus 0 is 0. And then 5 minus 2 minus 4 is 1 negative. And this one, S is 6 minus 3 minus 2, that's +1. C is still 0. And N is 5 minus 1 minus 6, that's -2. Sorry, I need to write the negative afterwards. Bad habit. So based on these 3 structures, you can eliminate one of these structures right away, which is the last one, because their formal charges aren't as close to 0 as possible. So that rules out that possible structure. Okay. Now here you have both structures have 2 zeros and 1 negative. To decide between those as a tiebreaker, if you're required to give a negative charge, is always on more electronegative atom. So, and conversely, the positive charge, if you have one, always goes on the least electronegative atom. Okay, so we have to refer to our electronegativity chart here to be able to see that. And I will put it up here just in case y'all forget about nitrogen versus sulfur. Nitrogen is 3.0 and sulfur is 2.5. So nitrogen gets the formal charge of -1 or 1 negative in this. So this is the preferred structure of SCN -1. I've seen this pop up on a lot of HL tests. Like they'll have a chart and they'll just have you calculate the formal charges of each element in each structure. And it's like a 4-mark question. So it's one of those things that you don't want to overlook, even though it seems like a very small thing, because it's in a very important topic of Lewis structures and stuff like that. It does tend to rear its head in some of these short answer questions. Like here are 2 possible structures, state and explain which structure is the preferred Lewis structure. So you have to talk about A, formal charge, and you'd probably want to actually say the values as well. And then B, if there's a tie break, you'd say, well, A is more appropriate because the negative charge is on the most electronegative atom. I've seen that question on previous papers before. If you've done some previous papers, you might have seen that question as well. So formal charge is a very big thing. Questions about that? Okay. Good news, I don't think there are any calculations in topic 3 or 13 that we have to do. So we will skip all the way down to topic 2 and 20 on 2 and 12. Okay. Now, there are the very kind of simple understanding things like mass number is equal to neutrons plus protons. You don't want to sleep on the fact of knowing your subatomic particles for each structure. So yeah, don't sleep on that, and make sure that you know a proton is also known as your atomic number. So don't forget that stuff while you're studying everything else. The main ideas of SL and HL here is light, the photons, the electromagnetic spectrum. And so understanding the following things, that C is equal to lambda nu. So the speed of light is equal to the wavelength times the frequency. Which means, because speed of light is a constant, that if wavelength goes up, frequency goes down. And understanding that relationship is really important. And for SL, you may have to calculate this and know that wavelength is in meters and frequencies in seconds to the -1 if you're going to plug it into this equation. Because speed of light is meters per second squared. Meters per second, not meters per second squared. So it's about units. You also need to know that energy equals h nu. Now, let me give you a caveat there. For SL, you just have to know the relationship, meaning that when frequency increases, energy increases. So you just have to know the relationship of, if I have a higher energy, I have a higher frequency, which is a shorter wavelength. If I have a long wavelength, then I have a low frequency, then I have a low energy. And then you also have to relate that to that kind of color wheel. ROY-G-BIV, Roy-G-BIV. And this is the lowest energy, and this is the highest. And it goes in this direction around here. And that's something you want to think about, but think about this. ultraviolet is very high energy. So the color in the visible spectrum that's closest to ultraviolet is violet. Infrared is lower energy. That's what you use for your remotes and like transmission of data and stuff like that. And that's going to be lower energy, so it can travel further distances. But so red is the lowest energy, violet is the highest energy. Now, for HL, you actually have to be able to use this equation where energy is equal to Planck's constant. Let me change the color here because I want to make sure it stands out. Planck's constant times frequency. Okay. And so with that, you have to know that this is energy of one photon. And I think that's where a lot of students make mistakes, because when they say like, what's the energy of what's the frequency of a photon used to break up a bond, people forget that bond enthalpy is kilojoules per mole. And this energy is joules per one photon. So you're going to have to do some conversions here to convert bond enthalpy to an energy value that can be used in this equation. And that's the hard part. Again, I be giving you equations and not telling you everything you need to know on how to use them. So if they ask for the wavelength of a photon that's needed to break a Cl to Cl bond, you have to take the bond enthalpy of C to Cl or Cl to Cl, convert it by dividing by Avogadro's number and multiplying by 1,000 to get the energy of one photon. And then you can use Planck's constant and frequency to figure out the frequency, and then you could use frequency to solve for the wavelength. But that's the big mistake that students make. They forget to convert the energy per one photon for this equation. Questions? Okay. Getting into the home stretch here. Okay. Topic 1 and 11. Actually, not really 11, sorry. It's really just topic 1, which is all the stoichiometry and stuff like that. Okay. And so I just realized I didn't do BOD. I will talk about BOD after. Actually, you know, I'll do that right now before I forget, because topic 1 is less important. BOD, SL and HL. Okay, that was the redox titration that I overlooked last time. So the main idea here is you need to know that 4 moles of S2O3 2- is the equivalent of 1 mole of O2. That's your mole to mole conversion that you will need to know to solve for BOD. Okay. Now I've seen some exams, they'll give you the reaction and have you figure it out. But if you already know it, then that will save you a bunch of time too, because it's always 4 to 1. But if you forget it, you can use the equations and kind of go step by step to logic it out. The other thing is you need to know that milligrams per decimeter cubed is equal to parts per million. So when you get the molarity, you have to convert it to milligrams to get the right parts per million. So if it's like 2.0 times 10 to the negative 4th moles per decimeter cubed of O2, you have to say like 1 mole of O2 is 32 grams, and then 1 gram is 1,000 milligrams. So that would be 6.4 parts per million left. Because when you do the Winkler method, you are trying to figure out how much oxygen's left in the water. Therefore, you can figure out how much was used up by the organic waste and bacteria in there. So you have to subtract that from the pure water value to figure out how much contamination is actually in there. So with BOD, those are kind of main calculations that you need to focus on. Milligrams per decimeter cubed to parts per million is equal to parts per million, and then also the 4:1 ratio for this as well. Questions? Okay. Sorry. Let's go into topic 1 right now. Okay. There are, I would say, it's probably about 4 different calculations in here. I would say there's gas laws, empirical formula, molecular formula. Stoichiometry, which includes percent yield. And limiting reactant. You could put limiting reactant in stoichiometry, but I'm going to kind of keep it separate because I want to address one thing about that. I may not go over all of stoichiometry right now because that's a little bit kind of more of a lesson, but I will talk about gas laws, empirical formula, and limiting reactant because there is a kind of a quick and easy way to figure out what's the limiting reactant without having to do all the calculations for it. If you're just trying to figure out what the limiting reactant is, there is a kind of quicker way to do it. If you did Rice charts last year, you probably already know the quicker way, but I'm going to show it to you anyways this year. Okay. Gas laws. And this is all SL and HL, by the way. There's no differentiation in this topic. Everyone needs to know this. Gas laws. 2 gas laws you need to know. PV equals nRT. P1 V1 over T1 equals P2 V2 over T2. And those equations essentially tell you all your relationships between gases and then also your ideal and being able to figure out how many moles of gas you actually have at certain conditions. This is really important because units are specific, meaning that you have to have decimeters cubed times, kPa or meters cubed times pascals. And over here, pressure and volume have to be the same unit, but temperature has to be in Kelvin. In fact, there's never a time in IB chemistry where you shouldn't calculate your value in Kelvin. Now, if it's change in temperature, it doesn't matter. You subtract and that's it. That's your change in temperature in Kelvin and your change in temperature in Celsius. But there's never a time where you ever really put in a Celsius value anywhere in your problem. So you should always be converting to Kelvin at the beginning for all these calculations. Empirical formula. Okay. With empirical formula, you're going to be given percentages or masses. And the idea is that you're trying to figure out the ratio of atoms in your molecule. And it's the only way you can compare amounts or quantities of substances in chemistry is in moles. So if they give you 75% by mass of chlorine, 35. Oh, sorry, it's chlorine, not chlorine 35. And then 25% by mass of, not chlorine, what am I doing? Sorry, carbon, and then hydrogen. But that did make me think that we need to do average atomic mass as well. Somehow I forgot that. Carbon and hydrogen here, that's essentially saying that out of a 100-gram sample, you have 75 grams of carbon and 25 grams of hydrogen. So to divide by the molar mass, you find that in that sample, you'd have 6.25 moles of carbon 25 moles of hydrogen, which means if you divide by the smallest number, you get a ratio of 1 to 4. So your empirical formula is CH4 in this case. Now, if you divide by the smallest number, you get a decimal. Depending on what that decimal is, you have to multiply by a number to get rid of that decimal. So if it's 0.5, you multiply everything by 2. If it's 0.33 or 0.66, you multiply everything by 3. Everything, not just that number, but every single value that you have so that the ratio stays the same. And when you want to find the molecular formula, you do the molecular mass divided by the empirical mass is equal to N. Okay. And so the mass of the molecular formula has to be a multiple of the empirical because they're proportionate to each other. So they might be the same, but it could be twice as big, 3 times as big, 4 times as big, 5 times as big. And the mass should reflect that. So when you divide the molecular mass by the empirical mass here, that tells you how many times you need to multiply the subscripts by. So like, let's say you have let's say you have, oh, that's fine. A molecular mass is 64 and this weighs 16. That means N equals 4. So the molecular formula would be C4H16. Now that's not a real molecule, but you get the point. You multiply the subscripts by that value that is the ratio between the two masses. Questions? Okay. While I'm here, average atomic mass. I don't know how I forgot that calculation. So when you have different isotopes with different abundances, you can solve for the weighted average or the average atomic mass based on those abundances for this. And so you might have something like, let's see, I'm just gonna, let's look up a problem real quickly and I will just use that. So for example, copper, okay? Copper has 2 major isotopes, copper 63, which has an abundance of 69.17, and copper 65, which has an abundance of 30.83%. And the way I do it, I think is foolproof because it eliminates a lot of the mental math that you have to do in your head. And so what I do is I multiply the percentage directly by the isotope mass for everything. And I divide by 100. And that's my mass. So 69.17 times 63 plus 30.83 times 65 divide by 100. And I get 63.62 for my average atomic mass. Which makes sense because it should be closer to 63 than 65 because you have more abundance of 63. So again, check your answer to see if it makes sense. If you got 64.6 or a number outside of 63 to 65 range, then you made a mistake. And so this is why I like doing it this way, because sometimes students either A, don't move the decimal point the right number of ways in their head when they're changing percentages, or B, when they see a decimal percentage, they don't also move the decimal point again for those decimal percentages because they think it's already a decimal, so they don't need to do anything. And so this way is foolproof because you're letting the work divide and convert the percentages for you into decimal form without you having to do it in your head. So you just divide everything by 100. As a side note, they might ask you to figure out the percentage of abundance of one of the elements. And you have to remember that X plus Y percentages equal 100. So Y could equal 100 minus X. So it's a little bit of algebra, and you'd plug it in and you'd solve for X, but you could solve for the percentages using this setup here. If you had the average atomic mass, which is given to you on the periodic table, and they told you there's 2 isotopes, you could figure out the abundance of each isotope to equate to that overall average atomic mass by using some algebra of setting X and then 100 minus X as your 2 percentages. Excuse me. Okay. Questions about that? Okay. One second. Okay. How to find the limiting reactant? The kind of fast way. Okay. The idea is this. Okay. Each reactant has essentially a value for it in terms of mole-to-mole ratios for every substance. And so, like when you have something like just simplified like this, if you have 6 moles of this and 2 moles of this, well, what you're saying is that 2 divided by 1 means like the kind of the change is going to be 2 here, and the change is going to be 3 here. Because for each unit of H2, you can make, sorry, for that amount of H2, you can make 3 units of a product. And with 2 moles of O2, you can make 2 units of the product. And so this is my limiting reactant, which then means that this, I can make 4 moles of H2O. So if I take the moles of each reactant and I divide it by the coefficient, whichever number is smaller, that's my limiting reactant. So you could have something like, I don't know, like C4H10 plus O2 yields CO2 plus H2O. And let's see, this is, I'm gonna have to double this. So 10 to 8, 16, that's 13. And let's say you had like 4 moles of this and you had 39 moles of this. Well, the net amount of product you can make is you can make 2 units of products times their coefficients. And here you can make 3 units times their product times coefficients. So therefore, this is your limiting reactant, and that will dictate your products. So I find the easiest way to do is solve for the moles of each reactant and divide by their coefficient. Whichever one makes a smaller number. So this is 4 divided by 2 is 2, and this is 39 divided by 13 is 3. So whichever one makes a smaller number, that's the one that's going to dictate your limiting reactant. And if you did Rice charts last year, then you can see that, because when you map this out as a Rice chart, your change is minus 2x, your change is minus 13x, your change is plus 8x and plus 10x. So if this is 4 and this is 39, you're essentially solving for x with the way that I'm doing it. So x could either be 2 or X could be 3. The problem is X can't be 3 because you can't have a negative number here. So X ends up being 2. So this is your limiting reactant. Then you do minus 13 times 2. So you have 13 moles left over. And then plus 8 times 2 is 16 of this. And plus 10 times 2 is 20 of this. And now you have the moles of all the products that you have present, and the reactants that you have left in the container after the reaction is completed. And so I find that's kind of a quick way to do it. Solve for the moles of each reactant, divide by the coefficient. Whichever one makes a smaller number, that's your limiting reactant. If you don't like that, you could solve for one of the products with each reactant, and whichever one makes less product, that's your limiting reactant as well. Just depends on how you want to approach it. But I just thought that for some of you that this might make a little more sense. It might be a little bit faster for you to solve for it. So take the moles of each and divide by the coefficient, and that gets you your kind of unit of reaction. And whichever one has a smaller unit of reaction is your limiting reactant. Questions? Okay. One last thing and we'll call it a day. Percent yield. Just a reminder, percent yield is actual over theoretical times 100. So the actual is your experimental value. So when you actually conduct the experiment, you are given a measurement of a value here. The theoretical is calculated. So when you do stoichiometry, that's always your theoretical. It's never your experimental. So that is one kind of last thing that I kind of want to talk about here for this. Actually, you know what? I'll throw in percent composition as well, because we talked about it briefly in the combustion analysis, but percent composition is the mass of element divided by mass of compound times 100. I guess we would do mass of element times the subscript. Times the mass of element. So for example, for H2O, it's 2 times 1.01 over 18.02. Or for C4H10, it's 4 times 12.01 over 58.14 times 100. And that percent composition is consistent with that compound. That percent composition never changes by mass. Okay. Any questions? Okay. That will end the recording for today. So I'm going to stop recording right now.